In this lecture, I will explain how we can do regression analysis in Stata. Let us open our file. I have my data in D drive. So I can, this area is command area, this area is results area. Here the variables will be listed with the names of variables and the labels of variables. This part also writes the same thing. Now, in order to open my file, which is in the drive, I will write the command use d. Now, my file name is us crime data, and the extension of stata files is dta. And therefore, I will just enter and I'll get my data file here. These are the variables. These are the names of the variables and these are labels. Now, if I click on this, again, this information is here and even the description of variables is here in terms of byte and whether it's a string variable, numeric variable, or is it a factor variable. Now I have data for 51 observations, 50 states plus DC. So that makes it total 51. Now these are the IDs of the same states, which I call SID. Now my variables are these. Now murder is my dependent variables or what's also called outcome variable. Now violent, urban, white, high school, poverty. These are my explanatory or independent variables. Now you may observe that here the labels give the description of the variable. Violent incidents are given in numbers, murder again in number, while urban population, white population, high school population, poverty in each of the states is in terms of percentages. Now before I start doing my regression, I think I should always save my file as a text file. For that, therefore, I create a file to save my results. Now, it's a log file. So log using and the drive in which I would like to save my file, it's a D. And then I can give some name for the file. Let's say US crime results. Dot text txt and then after comma again text. Now it's possible that I may have this file already saved and I don't want to continue with the results which are already given there. I want to replace it, therefore I have to write replace. If I want to add these results to the same file, then instead of replace I will write append. Now if I click it, enter it, that file has been created now. It will be a new file now and all my results will be saved in this file. Now this again, let me explain once again. These are various windows. This is your results window. Here you have variables. This is command window and whatever command you write here, they appear on this side here, the command. This is the review window. Later on, all these commands which you write, you can save them so that in future you don't have to write your commands here. You can just go to that particular command, highlight it and click it. So when you click it, your output appear on this screen. Now let's do the summary of our data. Now summary will give you the number of observation, it will give you mean, it will give you standard deviation and minimum and maximum. There are commands where if you want more information like for example median or kurtosis or skewness, that can also be done. Now, so here, let me write either summarize or sum. Now, I will write my dependent variable and then I will write independent variables. It can be in any sequence, but when you run regression, then of course, first you have to write your dependent variable and then followed by independent variables. Now, if I enter, I will get this information. So I have the variable names here. I have total observations, mean value, then we have standard deviation, and then minimum, maximum. Now, having done that, let me also run correlation to see the correlation between two variables at a time. So the command for that is corr, and now these are my variables. I can just copy them and paste here carefully. Now I will get a matrix of correlation. Now this is the correlation matrix. Now our observations are 51. Now you see that murder related to violent, urban, white, high school, and poverty. Now murder is my dependent variable, so I find that the violent incidents are highly correlated with number of murders. Even the urban population, if you have more urban population, it's related to murder positively. While the white population is negatively related, same is the education level. But again, poverty is significantly positively correlated with murder. So you can explain the relationship between any two variables in the similar manner. Now here we find that this correlation coefficient is 0.84, which is on the higher side. Perhaps we may suspect some kind of multicollinearity, which we can uh, do when we run the diagnostics of our regression, which will be subject matter of next lecture. Having done that, let's run our regression. So we write regression, or you can simply write reg, and then once again, you have to write dependent variable first, followed by independent variable. So I will simply copy this and paste it here. Now, once I do it, I will get regression output. So what do we find? We find a number of information in this table. Let's understand this table. Now here, these are some SS, okay? And then we have sum of squares. This is sum of squares. This is degree of freedom. Now here, when you are estimating your model, then the degree of freedom is your number of variables 1, 2, 3, 4, 5, 6 minus 1. And similarly, your degree of freedom in this case is number of observation, which is uh, 51, all right? And then from that 51, if you subtract the number of variables, and so you get your degree of freedom here. Now next, uh, this is your model sum of square. This is residual sum of square. This is total sum of square. And these are averages. These are averages. So what you find is that this is average. If you divide this number by 5, you shall get this number, and like that. And similarly here. Now, the output on this side really depends on your ANOVA table. This is called ANOVA table, all right? Now, what you do is, in order to find out F value will indicate you the fit of the entire model, irrespective of which variables are significant or which are not significant. Now, so F value will be simply given by this average, which we shall divide by this, and you shall get the F value in that case. Now, of course, this is probability of the F value which is given. Now, similarly, if you want to calculate r square, then you have this value divided by the total, and you shall get the this square of that r square. R square explains to you the R square will explain to you that the explanatory power of your model, that to what extent your independent variables are able to explain your dependent variable. So this is, let's call it A, B, and this is C, this is D, this is E, this is F. So that is how you decide about your uh, actually that is adjusted R square. Adjusted R square takes into account the degree of freedom. Now, similarly, you can calculate R square. Actually, R square is A divided by C. That is your model sum of squares divided by total. That is 1476.60 divided by 18.30. So I repeat again to be very clear about it, that when you calculate f value, then f value is given by two numbers, and that is given by your this one, this average, and divided by this average. So actually 295.32 divided by 7.83 gives you f value, and it indicates the degrees of freedom in terms of the variables as well as the number of observation, taking into account the degree of your variables, degree of freedom of variables. So that is your f value, and then of course from a table you can determine that how much is the probability. If this probability is less than 0.05, then there is a model fit. R square, on the other hand, when you calculate R square, it is your 14.76, this particular one, divided by the total of that. Okay, so this is the model sum of squares, this is the total one. So how much from the total you have, your model has been able to explain, that gives you R squared. Now here it's 0.867, so approximately 80% variation in your dependent variable has been explained by the independent variables. Adjusted R square, again, it from R square you can determine adjusted R square after taking into account the degrees of freedom. So that is this particular table, that these numbers are derived from the ANOVA table. Now, when we look at the coefficients of the variables and whether they are significant or not, now these are the important parameters which we need to look at. These are coefficients, and these are the standard errors of these coefficients. T value is in fact standard error divided by coefficient, and then again degree of freedom. So what we find is that this particular variable is significant at even 1%, so more than 5%. It's for 5% significant more. And this one is insignificant, while this is significant at 10% level. This is significant at 5%, 5%, and 5. And then constant term is also significant in this particular case. So that is how we explain our regression table. Now, let's look at little more closely to our data, some preliminary investigation, so that sets the stage for diagnostics. So let us look at that, how two variables are related. Are there some variables which are outliers, for example? Are there some variables which are not linearly related? You can get an idea by creating some graphs. Now here, if we create a graph of all variables together, so graph, we call it a matrix, and then we write all variables. Once again, I can just copy and paste it here. Now, if I just enter, what I will get is I will get two sides of my graph, left hand and right hand side, and the same variables relationship will appear on both sides. I just want to see at only one, not on both sides, just say one side. Therefore, I write half. When I do this, I get a graph like this. Now, if you expand this graph, what do you find? You find that this particular observation must be one of the states, perhaps. It seems to be an outlier in all the. It may be the same, it may be different, but perhaps it's the same one. Similarly, here you find that these two variables may be outlier, etc. So this gives you an idea. So our data may be suffering from outliers. This particular graph gives you that particular indication. You can do the same thing with regard to two variables at a time. So if I say scatter, and then I write my, let's say, the dependent variable followed by, let's say, one of the independent variable. Let me write, say, white population. Then, but I would like to identify which is the state or which is the ID of the state. So for example, if I have to write m label. So I want label to be named, and that is a state in this case, state. If I enter, then I get the names of the states. So DC is the state, for example, between these two variables. Now, similar graphs you can prepare for other combinations of dependent and independent variable. Now, if you want to, because your observations may be quite a few than just 51, and if you want to see the number, then you can do this this way. Let's see. So violent and murder. So I want to create a scatter graph between these two, and then instead of state, let me write m low, and this time I, let's say, write the uh, SID. Uh, in case of, let's say that if you are analyzing data of firms, so generally you write firm and then you don't write the names of the firms, rather you write 1, 2, 3, 4, etc. So SID is numbers actually. It's from 1 to 51. Each state has been assigned one identification, numeric identification. So this time you get that it is the 51 state. Okay. And if you go to your data, it is here. And if I look at here, let's say, and then if I see that which is the 51st state, now this is DC. DC is the first state. Here also you could say that if I look at the violent incidents, now this is quite way different from most of these observations. And that is also reflected in your the graphs. Now, for the time being, that's enough. And now what we do is that our file is already has saved these results. So I will log off. Now, if I log off instead of log close, I can resume recording or saving my results in future analysis with regard to the same data. So if I say log off, then my file will be closed for the time being, but later on if I write log close, then it will close completely and you will have to start with a new file when you do similar or different analysis on the same data.